Hi guys, welcome to this video on deriving the natural log function. Okay, so what we're after here is trying to be able to, looking at how to derive y equals the natural log of x and functions based on that, so composite functions as well. So we might have something like the natural log of, let's say, x to the power of 7 minus 2x, or we might have y equals the natural log of, let's go with the square root of x maybe times 2 plus 7x, maybe something like that would be some simple composite functions. Okay, so to do this, what we're going to have a look at for a start is the basic natural log function and how to derive that. So for a start, what we need to realize is that this is a shorthand for this fuller log statement here. So ln x is actually short for log base e of x. Now, one thing about logs is that they are simply a different way of representing an indices statement. So, for example, if I had the indices statement 10 to the power of 3, which we know is equal to 1,000, well, the equivalent log statement, the log of a number, the log of 1,000, is the power to which the base was raised. So that's equal to 3. But we need to indicate what base we're working in, and that's base 10 in this case. So if we did that in a more general sort of way, and I'll go with the notation which is in your book, textbook. So I'm going to y equals b to the power of x. That's an indices statement, so the equivalent log statement would be, okay, the log of what? The log of the number y is equal to the power to which the base is raised, so it's equal to x, and we need to indicate the base b. Notice b is the base of the indice here, so it's the base on the log statement as well. So there we've got a sort of general way of going from indice form to log form, and of course back the other way too if we need to. Now, so something equivalent in a sort of general way for that's connected with natural logs, as we'll see soon. Let's just have a look at what the equivalent would be for y equals e to the power of x. Now maybe thinking, well, why are we doing e to the power of x? Well, we'll see why soon, but we do know how to derive this kind of function because we just did that a period or so ago. Okay, so the equivalent log statement would be log base e of y is equal to x. Okay, and so if we take that, and then what are we going to go further with? Okay, so trying to tie this in with the work that we've done, let's go back to this thing that we're trying to derive. So we know that's y equals log base e of x, and if I put that into an indice form, we've got e is the base, be e to the power of y is equal to x, or in other words, x equals e to the power of y. Now, we have seen y equals e to the power of x. If I derive y with respect to x, if I use Leibniz's notation, which is going to be quite handy in this case here soon, we know that's equal to e to the power of x. It's its own derivative. Well, we can use this kind of idea here as well. I need to derive x with respect to y. There's nothing wrong with doing that. Okay, we're simply deriving this function that happens to have x at the front of it instead of y, and so we're deriving x with respect to y instead of y with respect to x. Now the solution for that would be e to the power of y. It would be its own derivative, just like we've seen with this kind of function here. Okay, so that's all very well, but what we do want to know is we want the derivative of this. So how are we going to get to that? Well, what we can do is we can take the reciprocal of both sides here. So I've got dy over dx is equal to, the reciprocal of this would be 1 over e to the power of y. E to the power of y is the same as e to the power of y over 1, therefore the reciprocal is this here. But we know that e to the power of y is equal to x. We've got that here, so we can substitute that. So we get dy over dx is equal to 1 over x. Okay, so what have we ended up with here? We've started with, this is what we're trying to derive, and I want to get dy over dx. And after getting dy over dx, okay, this is our answer here. So to summarize, if we've got y equals the natural log of x, its derivative, dy over dx, is equal to 1 over x. Okay, or y dash equals 1 over x. Okay, and so this is a small proof of how this is true. Okay, so rewriting it in log form, or explicit log base e form, rewriting that in indice form. Okay, just changing the order there, so x is at the front, deriving x with respect to y, and then using this result, which is similar to, analogous to, this one that we're trying to do here, this derivative here. So the derivative of x with respect to y would be e to the power of y. And then we take the reciprocal of both sides, and then we're going to go back and replace what e to the power of y is equal to in terms of x. Well, in fact, it turns out to be just x. So we end up with this basic derivative here. Okay, so what we need to look at next is, well, what about some composite functions based on this idea? Okay, so let's have a look at how we might derive some sort of composite function. Well, we're going to use the good old chain rule that we've used in the past with other composite functions. So if we've got the natural log of some other function of x, not just x, so let's do a simple example here. Y equals the natural log, and let's say of x squared minus 7x plus 2, let's say. Okay, well this is a composite function, so this is this gx part here. Okay, so what do we do? Well, according to the chain rule, essentially we derive the inner part here and then multiply that by the derivative of the outer part, where we treat the inner part just like a single variable for a moment. So essentially what that means is we derive g, which should be g dash x, whatever that function is, we derive it, and multiply that by the derivative of this natural log. And if you treat that just like a single variable for the moment, well, it would be 1 over that single variable, in this case 1 over gx. Okay, so there we've got, well, if we want to put it in more tidy form, we'd have g dash x over gx as the derivative. Okay, so coming back over here, we could say, well, our derivative then would be the derivative of the inner function, which is going to be 2x minus 7, because it's simply a polynomial, and we derive each part in turn, times 1 over the derivative, like so. So that's something we can tidy up just a little bit, I suppose. Okay, so that's a simple example, and we'll have a look at a couple more examples just in a moment. Alright guys, let's have a look at these two examples here. So let's take this one where you might have a number in front of the natural log. What do we do there? Well, what we're going to do is simply have the derivative, and it would be times -2. So let's see how that works out. So it'd be -2 times the derivative of the inner function, which would be 5x to the power of 4 minus 9x squared, some brackets needed there, times 1 over the derivative, 1 over this function here. So x to the power of 5 minus 3x cubed. Now, of course, that could be tidied up. So let's have a look at tidying it up. And of course, that was the derivative I found. So we could multiply out the -2 into this. So -10 x to the power of 4 plus 18x squared. Or you might argue, hey, it actually is quite alright just to leave it in this factorized or partially factorized format and write it like this would be perfectly acceptable. Okay, so just another example. What do you do if there's a coefficient or a number in front, I should say? Okay, then you're simply going to have your derivative times that -2. You may be wondering, well, why is that? Well, you could argue from the product rule for a moment. Let me just put down here the product rule. Remember this? F dash g plus g dash f. So if you treated -2 like function f and this natural log like function g, what you'd end up doing is you'd be saying, right, well, the derivative of -2 is 0 times whatever g is, that natural log x to the power of 5 minus 3x cubed, which is just going to be 0, of course, plus the derivative of the natural log, which we've just done here, this part. Okay, this part here, we've just done that, times f, which is that -2. So you end up with all of this going here. Okay, that is g dash times f. Okay, to save yourself quite a bit of extra writing, okay, the key thing to basically take out of this is that you derive the natural log function normally and you multiply that with the -2 at front. Okay, all right. Going to have a look at this other example here, and you think, well, that's so simple. Why do that one? Well, I want to show you how we could do our derivative work also using Leibniz's notation and a temporary substitution. And you may be wondering, well, why do that? It will be quite handy later on to be able to do this when questions get more difficult. So what I'm going to do is show you how Leibniz's notation would work. I'm going to let u equal this inner function here, 4x minus 2. And what happens when you do that is you can then simplify our y equals as y equals the natural log of u, similar to the natural log of x. Now, I want to be able to derive y with respect to x. That's what I'm after. And using Leibniz's form of the chain rule, I could derive y with respect to u, just derive this, times du over dx. Okay, and notice that if those sort of cancel similar to a fraction type situation, then we get dy over dx. So if I next to this put du over dx, that's deriving u with respect to x, would be 4, and dy over du, deriving this, would be 1 over u. We can then put those into here. Now, dy over du, that's just 1 over u, times, now du over dx, okay, is this 4 here, so we get 4 over u. And putting u back in terms of x would be 4x minus 2. Now that definitely can be simplified. It's a common factor of 2 top and bottom, so it simplifies to 2 over 2x minus 1. And you think, well, that's actually quite a lot of work, and wouldn't it have been simpler just to use Newton's form, which is derive that, which is 4 over that function, 4x minus 2, takes us straight to there. Absolutely true. But I just wanted to highlight for you how we can, if we need to, use this sort of substitution process and derive two separate functions here and tie them together with Leibniz's form of the chain rule to also get our answer. Okay, right, I think I'm going to do one more example and then I'm going to leave you guys to try and do some more. Okay, so I'm going to make a new page here. Oops, that's not what I wanted to do. And let's take a look at a last example where we might be using something like the product rule. So let's take something like, this one. Nx is equal to 3x minus 1 times the natural log of 5x squared. Okay, so what do we do here? Well, this is definitely an explicit product situation. We've got function f here, the 3x minus 1, times function g, which is this natural log function. So what we need to do to derive that would be the derivative of f times g plus the derivative of g times f, okay, i.e. product rule. Now what I like to do in this situation here is I like to derive each function separately. So that's what I'm going to do. Okay, so function f is equal to 3x minus 1. Its derivative is 3. Function g is this natural log function, and its derivative, using the work that we've just been doing, is the derivative of 5x squared, which is 10x, over 5x squared, which simplifies to 2 over x. X is cancelled down to just x on the bottom. 5 and 10 have a common factor of 5, so which we cancel that, having 2 just on top then. Okay, so coming back to our function n, what's its derivative? Well, according to the product rule, f dash 3 times function g, which is that one, plus the derivative of just realized up here there should have been g dash f. So coming back to here, that's f dash g plus g dash, which is 2 over x, times function f, which is that 3x minus 1, so we need brackets there. And can we tidy that up? A little bit maybe. 3 natural log 5x squared, maybe plus, I suppose we could write the 2x in front. Yeah, that would be okay, or we could also write this, which is also perfectly good. Okay, and that's our solution. So, yeah, have a go, guys, now at the questions on page 107 and 108, and we'll catch you next time.